Hello and welcome to the EGEV 2020 Space Studio. I'm here with Alexander Bock, myself, and tonight we will take you on a journey through space. We will use the interactive visualization software that we have developed and to browse the whole known. This journey is best enjoyed while sitting back with a glass of wine and company. So fasten your seatbelts and enjoy the pixels that will be streaming in high definition at 30 frames per second in sharp contrast to those coming from EGEV Space Team Alex. We will jump out into space and start our. Will take us a starting point and an altitude that is slightly above the city of Norrköping, where we are sitting, and you will see the building we're actually sitting in, and the Motala River flowing through the beautiful city that we're in. Let's start pulling back a little bit. See how we're gaining altitude, and we have a nice representation of the full Earth, the globe. We could essentially fly anywhere on Earth. Look at high resolution. The beautiful country of Sweden is coming into view with the Baltic Sea, the island of Gotland, Denmark, and the rest of Europe. We're paging in the atmosphere. What you're actually seeing now is weather that is as current as possible. These days we have, with the help of satellites that are orbiting the planet, we have daily weather, full coverage of the whole. So what you're seeing now is the Earth the way it looked like from space yesterday. What we will be doing now is to start look at some of the satellites. We humans, we have explored space, and we are constantly sending out more and more spacecrafts into orbit around our planet. We'll start by looking at some satellites that are orbiting us in low orbit, and we're turning on about the 100 brightest ones that you can see with a naked eye flying, especially on a late summer evening just after sunset. So you can see these satellites orbiting. They're going around the Earth in about 90 minutes at an altitude of about 400 kilometers above the surface. Now we're speeding up time a little bit. See how this swarm of satellites is moving. This is also the altitude of the International Space Station, ISS, where we have astronauts. And this is actually the only, at least semi-permanent presence of humans outside of the Earth's atmosphere. A little bit further out, we have other satellites that are very important to us humans, especially these days. That's the GPS navigation satellites that we are using to navigate. We are picking up the time signals from these satellites. They are synchronized using atomic clocks, and we are picking up the time signals down here, and we are calculating, compensating for general relativity. Thank you, Einstein, for helping us with that, to calculate with a few meters accuracy down on the surface of our planet where we are located. A little bit further out, we have a particular orbit called the geostationary orbit of satellites, where the orbital time is 24 hours, and that means that the satellites are stationary, so that they are actually seemingly standing still on the night sky. So this is what we use for satellite communication, satellite TV, etc. And this is an orbit that's quite densely populated as well. So as you can see, we have quite a few satellites out there that we humans have sent out over the past 50 to 60 years. Now, what we will be doing now is taking a huge step back in time, and we'll place ourselves at the launch date of Apollo 8, 68. The Cold War is on, the space race is on, and who is going to make it first to the moon? Apollo 8 is perhaps one of the most important missions in the space race, and we have managed to recreate the trajectory of Apollo 8. So the 21st of December, and right over Florida, you can now see in the visualization the trajectory of Apollo 8 as it's taking off. It will be orbiting the Earth twice, and then after that something that's called a translunar injection is happening, and they're firing the rocket to gain speed to escape the Earth. And this is the first time in the history of mankind when humans are actually leaving our planet to go to another celestial body, our moon. Now imagine the courage it took for these three men, it's Frank Borman, William Anders and Jim Lovell, to actually put themselves in the spacecraft and fly out into nowhere. And also imagine the skill it took to calculate this trajectory using very simple computers and the navigational instruments that had just been invented to be able to aim spacecraft towards the moon. It took 3 days, so on December 24th, Apollo 8 actually arrived on the moon. Just tweak our software a little bit so we will fly all the way. You can see how Apollo 8 is entering into an orbit around the moon. And the mission was really just to go around the moon 10 times and then return to Earth. And you can see we are still in the coordinate system of the Earth. So the moon is traveling and we are following around the moon in our spiraling motion in an orbit. And after 10 times around, firing the rockets again and going back home. Imagine how frustrating that must have been for the 3 astronauts to not be allowed to land on the moon. What we will do now is, since we have the trajectory, we will place ourselves, we will piggyback on Apollo 8, and we will place ourselves in the trajectory on the second orbit around the moon. What we also have is very high resolution imagery of the surface of the moon, captured by the Lunar Reconnaissance Orbiter almost 50 years later, with extremely high resolution, and you will see more of that in just a little. Here's Apollo 8. We also have synchronized the orbit with the sound, with the audio that was transmitted from Apollo 8 back to Earth as the astronauts were going. Now keep in mind, the main mission for the astronauts was really just to take pictures of the backside of the moon. But listen to them talking and see what happened as they were coming around the second time.
Ready? Set. The impact crater was at just prior to the subsolar point on the south side, and the floor of it nearly even, except there is one dark hole. But I couldn't get a quick enough look at it to see if it might be anything volcanic. Oh my God, look at that picture over there. There's the Earth coming up. Wow, is that pretty. Hey, don't take that, it's not scheduled. You got a color film, Jim? Hand me a roll of color quick,
Oh
will you?
man, that's great. Where is it?
Quick.
So you can all hear what they're saying. Little did they know that they were going to see this extraordinary view of the Earth rising over the horizon of them. And you can hear how they're also saying, hey, hand me the color film. That's actually William Anders who's asking Jim Lovell to give him the color film to take a picture of the Earth rising. They were not supposed to do that, but they did it anyway. They were supposed to take pictures of the moon. So let's actually look at the picture that was taken at this place. Now look at this. This amazing picture, perhaps one of the most important pictures that was taken in the previous century, indicating our place in the universe. I must also say that this is perhaps one of those times when we as Swedes can be very proud of the exploration of space, because that picture was taken with the Swedish camera, the Hasselblad camera. Now, the Apollo missions continued, and as you all know, in 1969, Neil Armstrong and Buzz Aldrin landed on the moon for the first time. But we are not going to go there to the Apollo 11 landing site. We will instead take you to Apollo 17. Apollo 17 is perhaps one of the most scientifically interesting missions to the moon. One of the main reasons for that is, of course, that one of the astronauts, Harrison Schmitt, was a scientist, a geologist, actually on the moon. And much of what we know about the geology of the moon comes from the experiments that took place during Apollo 17. So we are rotating around and we're looking at the beautiful constellation of Orion just behind. And we're searching for the landing site of Apollo 17. Keep in mind, we don't have any sophisticated navigational tools here, so we're relying on Alex's knowledge of the surface of the moon. Take us down to the Taurus-Littrow Valley, which was the landing site of Apollo 17. And again, we are using the images from the Lunar Reconnaissance Orbiter, and so everything that you're seeing is completely data-driven. And we are flying into the mountainous terrain and looking for the landing site of Apollo 17, which should be coming up into view pretty soon down here. Now, with the resolution of the LRO data, you can actually see the landing site. The little black dot in the middle right there is where Apollo 17 did. So now we're talking 1972, December 11th, 70. So this is I refrain from saying the last, but the latest time that humans have visited the moon. Now, one of the unique things about Apollo 17 is also, apart from the experimentation, they also had the lunar rover. So, and incidentally, we will show you a picture of what actually happened to one of the fenders on the lunar rover as they were unfolding it. A bit of a problem. So, a bit of engineering ingenuity. They took one of the maps that they had and some duct tape and fixed up a fender. It didn't work quite so well but at least the temporary fix that they did. Now, one of the amazing things about Apollo 17 is also the trips that they made. They drove all of 36 kilometers during the time that they spent on the moon. And what we have now is a map of the journeys that they made. You can see where you have solid lines on this map is where we actually know that they drove, and the dashed lines is where we have sort of guesstimates of where they drove with the rover. Excursions going in all directions towards the mountainous regions, towards the Tortilla Flat on the left-hand side over here. But we will be taking you to the North Massive, going straight up, and Alex will be zooming in on Station 6, and we will show you some interesting imagery from Station 6. What you can see is the tracks of a huge boulder, a big rock that has been rolling down the mountainside, and we can even page in some extra high-resolution data coming in here. And this is one of the famous sites where there's a lot of video footage and imagery from this particular site. You can see the LRV where the rover is parked, where they took the panoramas, the north panorama and the south panorama. And what we will do now is actually page in for you images that were taken right on this site. So here you go. Here's the rock called the Split Rock. You can see why it's called the Split Rock, and you see one of the astronauts taking samples of the rock and the rover parked on the other side. And what you can even do is to match the horizon with the images that we're seeing here. And now keep in mind that what you're seeing is data that has been captured using the LRO, and you see pictures taken in the 1970s using the Hasselblad camera. We're matching the horizon. So if there are any conspiracy theory people out there, this is some sort of evidence that humans have actually been on the moon. Now, we will take off and we will leave the moon behind us. We could spend hours and hours and hours exploring the moon, going to different sites. It's scientifically extremely interesting, but it's sort of black and white. What we will do now instead is we will take off and go out into space, and You know, the moon, it took 4 days, 3 days, 4 days to travel to the moon. If we're looking at traveling to Mars, it would take us 9 months approximately on a fast journey. And of course, this is the next stop for humans. Mars has been explored, and many people don't know this, but already back in 1964, the first flyby of a human spacecraft took place, the Mariner 4. And you can see we're getting close to Mars here. You see the 2 moons, you see Phobos and Deimos, and you can see Mars. Now, what we have, just as we had the LRO orbiting the moon, we had a spacecraft called the MRO, the Mars Reconnaissance Orbiter. And there are instruments with varying resolutions on the MRO. One is called the CTX camera, the context camera. And what we have from the context camera is patches of data with 6-meter resolution over the surface of Mars. Now, Mars is very exciting in many ways. We have the tallest mountain in the solar system is on Mars. It's Mount Olympus. It's 26 kilometers tall. And we have this very interesting region called Valles Marineris, and we're heading towards that at this point. It's sort of the Grand Canyon going across the surface of Mars. The Martian atmosphere is very thin, and it consists almost entirely of carbon dioxide, 96% carbon dioxide. And the temperature is not so nice. We can, on a warm sunny day, we can get almost Earth-like temperatures, but it's very, very cold and lots of frozen carbon dioxide. Now, the region that we're heading into is the Valles Marineris, and one particular site on Mars that we are moving into. And this is the southwestern Chondrocosma. And what Alex is doing now is that he's paging in data coming from another instrument of the MRO called the HiRISE camera. And the HiRISE camera gives us resolution of about 25 centimeters. So what you're seeing now is the Martian terrain almost down to the human scale. Those sand dunes that you see in front of you are maybe 50 to 100 meters altitude. And we are slowly flying across the domain and becoming the data explorers of an unknown part of the alien planet. The formations that you see are created by possibly water flowing here, wind blowing, so it looks like the sand dunes on a beach on planet Earth after stormy. After a short excursion of Mars, we will again take off into space, and we will fly out to a distance a little bit away from Mars, and we will start looking at some other very exciting, interesting data that we have out here. As you all know, we have not only planets in the solar system, we have lots of other smaller bodies, and in particular we will be looking at the asteroid belt. And we have databases that are indicating many of the asteroids here. And we are flicking through the menus here to pick out the right data sets for you. We start by looking at a subset of asteroids that are in our databases indicated as potentially hazardous. So here we have the rocks that are more than 140 meters in diameter, with a probability of getting within 20 orbits, radius orbits of the moon of Earth. That means that they are potentially hazardous to us, so that if they collide with Earth, it could cause an event like the big extinction of the dinosaurs. So we have to watch out for those. But as we all know, we can trust the Americans to take care of that, especially Bruce Willis can fly out there and blow up these asteroids for us. If we turn on the full data set of asteroids, you will see that there's quite a few of bodies up. It's almost saturating the visualization here. Yeah, that's enough, Alex. All right. So let's pull out, and we could visit essentially any of the planets in the solar system, but what we will be doing now is to pull out and get a little bit of a perspective. Now, we will have to use the speed of light as a measurement. it takes 8 minutes for light to travel from the sun to us, to planet Earth. Where we are now, when we are leaving the solar system, we have a distance of maybe even a light day, 24 light hours. And that means that also radio signals will take 24 hours to travel back to Earth from here. So radio communication has a 24-hour lag. So what we'll be turning on now is trajectories of two kinds of spacecrafts that were sent out in the 1970s, 1972 through 1977. The Pioneer 10 and 11, 72 and 73. Those are the red lines that you're seeing here. You can also see the kinks in the lines. That's how they've been slingshotting around the big planets to gain velocity, like Jupiter. And we'll also turn on Voyager, Voyager 1 and 2. And the yellow line is going up. Now look at this image here and keep in mind that this is the footprint of mankind in terms of objects, man-made objects. This is as far out as they have come. This is as far as we have made ourselves known. Now, we still have radio contact with the Voyagers because of the thermonuclear reactors on board generating enough power to transmit signals. And we have indicated, we have read that the Voyagers have left the heliosphere, they have left the solar system in 2012 and in 2018. Now keep that in mind as we're pulling out, because we are now moving towards a light week away, and maybe even a light month, going faster and faster and faster in space. And we're stopping at about a light year away from the sun. Here we will be turning on the constellations, and what you're seeing in the background is the stars in the Hipparcos catalog. And with a naked eye on a very dark night, you can see maybe 5,000 stars, and you can see the constellations. And we turn them on here, and I think we're actually looking a bit in the south. There's the Swan, and there's Vega, the blue star, right? There's the North Star, right hand side. Big Dipper, the blue. Now, the constellations are tying together stars that are located at very different distances away from us. So as we're pulling out, you will see how the constellations actually are being distorted. Now we're moving in three-dimensional interstellar space, and the constellations, they just turn each hedgehog of lines. Our nearest neighbor, Alpha Centauri, is flying by, and we are moving out towards a distance of maybe 60 light years away. Out here is a good point to turn on another representation that we have in our visualization, and that is what we call the radiosphere. The radiosphere indicates how far out the first radio signals that were strong enough to penetrate the Earth's atmosphere and the ionosphere and propagate out into space. This is as far as they have come. We talk about radio transmissions, experimental television broadcasts from the 1930s. The opening speech at the Olympic Games in 1936 is one of the examples that Carl Sagan, the famous astronomer, used as an example of this. What we are all wondering, of course, is there life out here? Is there life that could potentially have picked up any of these radio signals that are out? If there's life, there's probably life on planets. Are there planets out here? And the answer to that question is yes. Now, what we're turning on here is exoplanets. So each of the stars that now has a ring around it, we know that there are planets. Exoplanets is a fairly recent discovery, and there are more and more coming into our databases as the years go by. We have more than 4,000 at this point. Planetary systems that we look at. Quite a few of them are inside of the radiosphere. And even Earth-like planets have been discovered in the habitable zone around the star. As we're moving out, keep an eye on the radiosphere. Look at the haze of stars that's coming into view. 200, 300, maybe soon 1,000 light years away. And you're beginning to see the structure of our galaxy, the Milky Way, where we have 110,000 light years across from one side to the other side. Maybe 300 billion stars in the As we're pulling out, we're beginning to see other things in the background. That is, of course, other galaxies. Each of the points now is another galaxy. So imagine we may have perhaps several 100 billion stars in each of these points that you see. The data that you're looking at is the Tully data set of galaxies. It's a catalog that was published the first time in 1980. 68,000 galaxies inside of it, and it's stretching out to a distance of about 700 million light years. But that's not the end of the universe. As we're pulling outside of the Tully data set, we're beginning to page in data from the Sloan Digital Sky Survey, where we have charted out the universe in directions. You can see the sort of dark region in the middle. That's actually the shadow of the Milky Way, because it's hard to observe galaxies, distant galaxies, in the plane of the Milky Way because of the stars and all the dust particles. You can see the directions where we had campaigns in the Digital Sky Survey. We have more than 1 billion objects that we're looking. The Sloan Digital Sky Survey is continuing and capturing more and more data, not only positional and luminosity, but also spectral data out here. Very exciting. More data is coming in. Now, one of the things we have to stop and look at and reflect over here is that when we're at this distance of, say, 6 billion light years away, we are looking at data, light that has been propagating towards us for maybe 6 billion years. So we are actually looking at the universe the way it looked like 6 billion years ago. Now, you may think of this visualization as non-physical, and in some sense it is, because we have connected space and time in this visualization. But everything has been collected through the viewpoint of the Earth. So as we're pulling back, we are moving backwards in time. And in fact, when we reach this distance out here, we're looking at the early universe, the young galaxies in the universe, and also at another kind of objects that are peaking at a distance of about 10 billion light years away, called quasars. Now, quasars were discovered the first time in the late 1950s and really puzzled the astronomers. What are these objects that are so far away and redshifted so much so that they're moving away from us at very, very high speeds? Well, it turns out that it's probably gigantic black holes, and there's matter falling into the black holes, and then in this collapse, generating a lot of radiation. A little bit further out, we're beginning to see the very, very early universe. Approximately 13.8 billion years ago, the universe was created in the Big Bang. A few 100,000 years after that, the universe became transparent in a recombination event when electrons met protons for the first time, and the photons could bounce around and not be stopped by scattering. This is what we're seeing here. This is what we call the background radiation, and the map you're seeing is the Planck map, the most recent mapping of the cosmic background radiation. This sort of indicates the end of the universe, the end of the known universe, because we will never be able to see anything beyond the edge of the background radiation. Because if we were to see things there, we would see things that are actually older than the universe itself. And of course that's not possible. So from our point of view in the universe, this is the end. In visualization, the physical boundaries are not stopping us from moving outside of the universe, so we will actually pull you outside. And here you see the ball that we call the known universe. My personal view is that this is perhaps one of the most amazing accomplishments of mankind, that we have been able to measure all these distances by looking at planets, looking at nearby stars, triangulation, variable stars, redshifts, and putting it all together into a consistent map of the whole universe, and create this digital twin, a virtual copy of the universe that we can navigate using visualization tools. I hope that you have enjoyed this journey out to the end of the universe. And I would like to invite you to discuss this with me. And I will join one of the chat rooms here in a few minutes. And if you have any comments or questions, we can talk about that on the Discord channels. But from Alex and me, I can't think of a better place to leave you halfway through this conference here outside of the universe. So we'll end our show here, and thank you for tuning in, and we hope that you enjoy this. And to Johanna, I hope that your cat is still awake. Thank you and good night.